So, we are talking about energy method. Talking about means just we have started talking on this. The technique is energy method. It is based on basically the concept of strain energy. The strain energy we are trying to explain in with the form of a simple bar problem under tension. All right. So, we took a bar in that form and applied a load P. Now, this is a case of a very simple stress problem, because entire bar will have identical stress and strain. So, anywhere stress is P by A and strain will be your total elongation divided by length of the member. So, it is a case of uniform strain, uniform stress, whatever you can say. Now, the elongation we wrote in the last class, it was P L by A E, and we have drawn a curve like this, your load versus elongation, straight line, because whole thing is a linear system. And for any load, if you start applying load from 0, gradually increase, go up to a load P, the elongation will increase from 0 to delta, and the area under this load deflection curve we have found that it is basically the work carried out the force P. Now, it is not straight away P and delta, because P is not constant throughout, because P is starting from 0 to that P, and it is delta is starting from 0 to delta. So, total work, so that we have put in the form of half P into delta. Right. So, that work, it will be stored in the form of some energy, we said strain energy, that strain energy will be equal to this work done half P into delta. Now, here load why we are putting in a gradual manner, because we want to maintain the static condition. If we apply suddenly load, whole thing will be a dynamic problem. So, that will be much more difficult case. So, we want to understand with a very simple type of problem. So, load in a static manner, if we want to apply, we have to apply gradually. So, always there will be balance between internal and external force system. Basically, the strain energy, though it is expressed in the form of P into delta, it is rather the measure of some internal quantities. Internal quantities means there will be deformation that we define in the form of strain, and due to the strain some stress will be there. So, whole thing is a measure of the strain and stress inside. And you must have remember, we have written this one as this sigma epsilon into V, because that P we have divided by area, epsilon divided by L. So, it became stress, it became strain, and this L and A, it becomes V, that is the volume, or sometimes we write it is U0 V. So, U0 is this part, we sometimes say it is strain energy density, right. So, half stress into strain is the strain energy density multiplied by the volume will be the total energy. Now, this is a case of uniform stress and strain. So, everywhere your sigma and epsilon is constant. For a general case, we have written U equal to your half sigma epsilon dV, right. Whereas, this was written for a case for a arbitrary type of problem where stress strain will vary from point to point. So, this is valid for this problem where stress strain is uniform. So, if we take a case where stress strain is not uniform, it is varying. So, this concept is valid for a small point, for a small element. So, that concept applied, say V became dV. So all the element if we combined, so we are supposed to get the expression of strain energy is equal to U equal to half integration sigma epsilon dV. Now it is basically strain energy, so related to strain or related to stress, so it is basically internal thing. Though we have tried to explain at the beginning in terms of external work, because external work, internal work in the form of strain energy, we have tried to equate for applying a load in a gradual manner in a static condition. But this strain energy concept is valid for dynamic problem also. If we apply a load, your internal stress strain, it will gradually increase from 0 to a certain value. So it will not be suddenly generated. So this half term will be coming there. Only thing, the internal system and external system will not be in equilibrium. Naturally it will be in a moving condition, in a dynamic condition. Otherwise this concept will be there. So for a expression of energy in a generalized form, we can say U equal to half sigma epsilon dV. Now here number of stress component is 1, number of strain component is 1, because it is a one dimensional problem. If we have a stress analysis problem where number of stress component is more, say if we take a plate, it is under stretching, so it will be a biaxial system of stress, so it will be a plane stress type of problem. So there will be 3 stress component, 2 normal stress component, one along x, another y, plus shear stress. Similarly 3 strain components will be there. So in that case we can define sigma x multiplied by epsilon x plus sigma y multiplied by epsilon y plus your tau xy into gamma xy. So for a specific case we can write in this form for a biaxial system of force, say it is sigma x epsilon x, sigma y epsilon y, tau xy gamma xy, right, into dV. Say if we take a thin plate, we can take it is dx dy, and we can multiply it by thickness. T is the thickness of the plate. So this is a special case of strain energy for a stress problem where number of stress components are more. So this idea can be generalized. Now at this moment we are interested with simple problems, so it is only one component of stress. Now this expression of strain energy we want to apply directly to a bending problem, because we are handling a problem having some bending of the beam or bending of the frame member. So bending part we are mostly dealing at this moment. So this strain energy if we put in a bending mode, so what will be happening? So if we write strain energy in bending, we know any member if it is under bending we will get bending stress, and that bending stress it will vary from lower fiber to upper fiber in a gradual manner. It follows a linear manner. At neutral axis it is basically 0 and it will increase if we go away from the neutral axis. So along the depth direction it will vary, and along the width normally we assume it is uniform. So depth wise variation is there, width wise variation is not there, plus along the length bending moment will vary, naturally it will vary. So if we think in terms of x, y, z, along length it will vary, along depth it will vary, along width it will be constant. So it is not a uniform state of stress for the bending stress component, right. Now in bending there is only one stress component, that is a bending stress. Now due to shear or shear force there will be a shear stress, but due to shear stress we do not consider any shear strain, right. In elementary bending theory the effect of shear deformation normally we do not consider. This is one of the assumptions, because the beam theory, what we have the understanding, we assume a plane perpendicular to the neutral axis before bending remain straight and normal to the deflected neutral plane or neutral line after bending. So, that assumption is based on that idea that we are not considering the effect of shear deformation, because shear stress it varies in a parabolic manner. If you take the effect of shear deformation, so it will be not a normal line, okay. It will not be a straight line and it will not be normal. So, that normality will be violated, plus it will have a warping of the whole section. Normally what happens, if we take a beam, its length is quite the value of the length, normally it is higher compared to the depth and width of the beam. Now, that is mostly common in our structural member. Now, in that mode, so bending is predominant, right. So, bending deformation is predominant, the effect of shear deformation is little less. Just if we take a case, say there is a structure like this, there is a support, there is a support, and if we put some load here, so a long member under load, so bending will be predominant. Now, if we try to shift the supports, so if you shift the supports, if support is here, support is here, so this support will be shifted here, this support will be shifted here, your bending deformation will reduce. In one case, say the support, both the supports will be tending towards the load. So, there are two supports, there is a load. What will be the mode of failure? It will be just, it is shear mode of failure. Just we can think, there is a cantilever beam, or same this problem we can think in terms of cantilever. If we put a load here, it will try to bend. Now, if you try to bring it here, if you bring it here, what will be happening? So, there will be certain shear of the whole thing, but if you put the load here, it will undergo bending. So, fiber will start failing gradually from top or bottom, but here once the length will be reduced. So, it depends basically the depth versus this length. So, once this length is more compared to this, bending will be predominant. If this length is very small compared to this, so it will be in shear mode. We cut a piece of paper by scissor, okay, means two forces we are putting more or less on the same point with a slight shifting. So, if we put two blades, it will never cut, it will be under bending, okay. So, when length is more, your bending aspect will be predominant. When length will be small, it will be in shear mode. Just shearing of the rivet, two plates with a rivet, if you try to pull, practically there is no gap, so it will shear. But if you place here, there is a long neck, two plate, so whole thing will try to bend, right. So, it depends what is the size of our structure. So, normally our structural member will have a large span compared to the depth. So, bending will be predominant, and normally we take the deformation due to the bending action. So, bending stress will produce bending strain, and shear stress will be there, but shear strain will be very small, and if you count, if it is say 1% or less than 1%, there is no point of making the analysis very complicated, because we have to take the effect of shear, some other expression will be coming into our equation, we have to handle that, and maximum benefit we will get say 1% or 0.5% if the span is quite large. So, we do not consider that. So, in bending mode, basically though there are two stresses, but the strain due to the bending part will be predominant, that is why we take the bending strain only, we do not consider the shear strain. Shear strain means strain produced by the shear stress. So, two stresses and two strains. So, one of the strain is basically 0 and energy is stress into strain. So, energy due to the shear force, shear stress, shear strain, this part we can simply neglect. So, it will be a one dimensional problem, means it is a problem with only one stress component, that is a bending stress and its corresponding bending strain. Now, the second aspect is the stress components will vary, as I have mentioned, it will vary along the depth, along the length, only width wise we are keeping it more or less uniform. Now, if we write the energy, so U already we have written, it is sigma epsilon dV, we can write dx dy dz, right. So, dV is dx dy dz. So, we are putting it in a separate form, and here this sigma for a bending problem we know it is my by I, right. So, it is depending on y. So, if x is the length, x is the coordinate along the length of the member, along the axis of the member, y is perpendicular to that along the depth, and z is along the width. So, sigma we can write my by I. Now, here if I put the expression of sigma, now what we will get? Now, strain is also dependent on stress, right. So, strain is just stress by E. So, this expression can be defined in terms of stress entirely, or it can be defined entirely in terms of strain. So, this sigma we can write as E into strain. So, it will be totally strain dependent, or this we can express in the form of sigma by E. So, it will be entirely stress dependent, but here we know the expression of stress. So, it is better to write in the form of stress. So, we can write in the second step half, it is epsilon square divided by E dx dy dz, right. So, it will be sigma square divided by E into dx dy dz. Now, here we will put the value of sigma, that is my by I. So, if I go to the next page, so we can write u equal to half integral. So, it is sigma square, means it will be m square y square I square, denominator E is there. So, dx dy dz. Now, this half, this m square by I square E. Here you just observe I E, more or less this quantity will be a constant quantity. Here m, it will be fixed at a station for a particular value of x, it is constant. So, if we integrate about y and z, so y z mean along the cross section of the member, because this is x, it is y, it is z. So, along the cross section if we integrate, so along the cross section means at a particular station m, it will be constant. So, m will vary from one station to another station. So, here we can integrate. So, if we integrate about dy dz, about yz, so here y square will be coming into the equation. So, it is what dy dz, if we write it is dA. So, integration y square dA is what? Second moment of area. So, we can write this one as I dx, right. So, this one and this one if we handle y square dy dz, so that will lead to your I, right. Now, this I and this I will cancel. So, it will be your m square by EI dx. Rather, this is a very common expression for the energy in bending, right. So, we have started with u equal to half sigma epsilon dx dy dz. Epsilon we have expressed in the form of sigma by E, and the sigma we have written my by I. So, this y square dy dz, so that part is simply I. So, ultimately it will lead to m square ei dx integral half, it will be the energy, right. Now, for bending mode, so whatever bending moment is there, square of that divided by ei into dx half, that will be the u. Now, if you try to compare with your basic expression of strain energy, that was half sigma into epsilon into dx. Here sigma you can think the analogous term of sigma is bending moment m, and m square is m into m. You can write this m into m by ei. M by ei is what? d2y by dx square. So, d2y by dx square is what? Curvature, right, and d2y by dx square curvature multiplied by ei is equal to moment. So, we can say moment curvature with a relation with a factor ei. So, ei is just like your E, and d2y by dx curvature is strain, and this is stress. So, it is not stress, it is stress resultant, and curvature is not the strain, it is a generalized curvature. So, that thing in this form we are trying to express, right. Once that is there, the energy of a beam under bending. Now, there is a theorem of energy in terms of calculating the deflection, and that theorem we have defined as the energy theorem, and that was first proposed by Castigliano. We say it is Castigliano's theorem. So, Castigliano. So, the energy principle is based on the theory proposed by Castigliano. We say it is Castigliano's theorem. So, what is that theorem? Basically, Castigliano has two theorems, or the whatever he has proposed, it has two components. So, one of the component it will be utilized here. So, if we say u, if we write the Castigliano's theorem, so you can express the energy of the system, we can express in the form of the forces, right, because the energy here, energy is half m square ei dx. So, if we take a beam problem, m we can find p into x omega x square by 2 something. So, it will be expressed in the form of some force, right. Now, it can be also expressed in the form of displacement, right. Now, we are interested for the force part. So, u, if it is a function and it is defined in terms of some force, it may be one force, it may be a number of forces. So, there is a beam problem, it is subjected to P1, P2, P3, P4 like this. So, the bending for the different region you can express in the form of, because reaction will be in terms of P1, P2, P3, P4, Pn, and that reaction into that distance, then the force into some distance, automatically the moment expression will be in the form of P1, P2, P3, P4, Pn, and energy expression is nothing but your m square ei dx dy. So, whole thing will be expressed in the form of these forces. Now, once that expression will be available, now if we take partial derivative about u for P1, we will get delta 1, or if we just P2, it will be delta 2, or like this Pn, it will be delta n. Now, if the force is only 1 P, so energy will be expressed in terms of P. So, partial derivative will be full derivative, right. So, it will be du by dp will be delta. So, what is delta? Delta is the deflection under the load P1, right. So, delta 1 is deflection under P1, delta 2 is deflection under P2. I think if I draw a figure, it will be better. Say it is P1, if it is P2, if it is P3, this will be your delta 1, this will be delta 2, this will be delta 3, like this. So, here I have just drawn any arbitrary beam subjected to P1, P2, P3. So, reactions can be evaluated in the form of P1, P2, P3. So, moment expression you can find out in terms of P1, P2, P3. So, if moment is in terms of P1, P2, P3, ultimately your energy will be a function of P1, P2, P3. Now, if you take derivative of u in terms of P1, you will get delta 1. Delta 1 is the deflection under the load, and delta 2 is deflection under the load P2. Delta 3 is the deflection under the load P3. Like that you will get. So, if there is only one load P, so if you take the derivative about that P, you will get the deflection under that load, right. Now, see, there might be a question, at the middle there is no load and we want to get the deflection here. Is the theory valid there? Should I apply this? Definitely we can apply. Here we have to put a load, say P at the center, and we will apply this theorem. At the end we will put Pc is equal to 0, right. So, we will put Pc as an unknown and apply this theorem. Actually Pc, there is no force, so this value will be 0. At the end we have to apply, but initially we have to take it, otherwise you can proceed. I think those part, if we take some example, it will be much more clear. Okay. Say you start with the problem which already we have solved by other method, we know the result. Say it is a cantilever beam, it is subjected to load P, right. It has some length L, some E, some I, something is there. So, length is L, E is the material property, I is the second moment of area. Now, due to that load, say deflection under the load we are interested, right. So, first job is we have to find out the expression of the bending moment. Now, you can start x from this way or from x from that side. So, it is better to start from this side because expression will be much more easier, P into x. This side it will be P into L minus x. So, if we start x from here, so m will be your P into x, and our energy is half EI dx. What is m square EI by dx? It will be half P square x square EI dx, limit will be 0 to L, right. So, entire span, it is the expression. Now, this advantage we may not get in other cases. If we put a separate load, moment expression will be different. So, the integration will be performed say 0 to L by 2, L by 2 to L, like this. Now, this integration if we perform, so it will be there are two options. We can perform the integration, after that we can take the derivative, other option is we can take the derivative. So, there are two options. Now, it will give the same result, right. Say we put it in that manner, say half m square part we can write as m into m, right, or let us put the derivative first, du by dp, that will be the delta. Now, if you take the derivative, so here what will be happen? Here p square will be there, p square will be 2p, right, or this expression we can little bit change, that will be easier to understand. P square x square we can write as p into x, right. So, here moment is p into x whole square of that ei dx. Now, delta du by dp, it will be, the square term will be 2 into that px. So, here this 2 if you bring outside, so it will be px plus derivative of px will be, in terms of p will be x. We are taking derivative about p, not about x. So, that divided by ei into dx, and definitely it will be 0 to L. So, our energy half m square ei dx. So, half here m we just put px whole square. Now, delta is derivative of u about p. So, this part 2 we have taken out. So, 2 and 2 it will cancel, and this will be the px and it will be x. Now, what is this? This px is basically m and x is derivative of m with respect to p, right. So, it is derivative of m with respect to p. Okay. So, that part we can explain later also. So, that will be the expression. Now, if that is the expression, so it is px square divided by ei into dx. So, it will be p if we take out, ei if we take out, it is basically integral dx 0 to L. So, integral 0 to L x square dx will be your x cube by 3, and limit if you put it will be L cube by 3, other part 0, it will be cancelled. So, whole thing will be leading to p L cube 3 ei, and that expression we have determined by moment area theorem or differential equation technique. It is a standard expression. So, here we obtain through your energy principle. We have written the expression of m under u, we have put there and taken derivative. Right. Now, I shall take a different case, what I was trying to tell little bit earlier. Say there is a similar type of cantilever beam, but it is subjected to a distributed load omega, and we are interested to finding out the deflection here under the free end. There is no load. In that case, there is a load, under the load we have calculated the deflection. Now, just talking about the simply supported beam, mid-span deflection, no load. So, more or less similar situation, fully distributed load we want to find out, and practically there is no physical load there. Okay. Now, this problem we will just put a force here P, and this force is nothing but will be equal to 0. right. Now, in a similar manner, if we take x axis from this side, we will have a moment expression of m of p x omega x square divided by 2. At any x, it is p into x into omega x square by 2. It will be plus. Both are in the same direction. Now, this p is 0. So, at the beginning, if I put p equal to 0, this part will not be there. Why it is important? That if we carry out that problem, it will give that feeling. So, our u is equal to half m square ei dx, that part we know. So, we can write here, it is p x So, just I have substituted the value of m px plus omega x square by 2 here. Okay. Now, next job is one option is we can perform the integration, finally take the derivative. Other option is we can take the derivative and then perform the integration. I think second option is better. So, delta, it should be du by dp. Now, this will be half. So, this 2 will come out and here it will be px omega x square by 2. So, we are taking derivative of that quantity. So, it was square 2 into that quantity 2, we are putting it outside, and we have to take the derivative of this quantity with respect to p. So, it will be straight away x divided by ei dx, right. So, this term was with square. Now, we are taking derivative of that. So, something square, it will be 2 into that quantity plus inside quantity you have to take derivative. So, that internal quantity if you take derivative out p, so it will be simply x, this part it will be constant, say W may be 10 kilonewton per meter or something. Okay. So, it is not a variable quantity. Now, at this level, now you can go ahead with the integration, or at this level we can substitute p is equal to 0. Before that you have to keep p, because this part we have taken square. So, it is there after derivative. Now, once the internal part we have taken derivative, we are getting x. So, x it is coming from px, and px is this one, though this part is not there, p is equal to 0. So, at the beginning if we put 0, if we take derivative nothing will come. So, artificially we have to put a p and it will carry, so it will give x here, right. So, at this level we can substitute 0, or we can integrate, later on we can put 0, anything you can make it. Now, so let us keep it. So, this will cancel. So, it will be one part will be we can say, so let us put the integral, it will be p x square, another part is omega x cube divided by 2 whole quantity divided by ei into dx, or we can write it will be p L cube divided by 3i plus. So, this x square will be x cube divided by 3. If we put the limit, it will be L cube by 3 divided by ei, and here this omega xq will be x4 divided by 4, right. So, it will be omega L4 divided by 8 EI. Right. Now, now at this level we can make P is equal to 0. So, this part will be the deflection. So, what will be the deflection? How much we have derived earlier? It is, we can check it, okay, no problem. It is okay. It is 80. So, it is okay. So, I was suspecting there might be some, because we are calculating, if we drop some 2, so whole thing will be a different value. Now, the actual problem was omega, and the deflection under the load, it should be W L to the power 4 divided by 8 EI. Now, this will be equal to because your P is equal to 0, right. Now, I kept it intentionally because in previous problem we have determined that deflection is PLQ by 3I. So, this PLQ by 3I part is also there. Say beam is subjected to this load plus this load, omega plus P. So, this part is due to the load, point load, this part is due to uniformly distributed load. Now, if that part is not there, it will be dropped out. If that part is there, so this is the value. So, I could put it 0 earlier, okay. So, we need not carry out one of the component. So, unnecessarily I have kept it, just get the feeling that this part is also there, it will come out, okay. Okay. So, the objective of taking this problem is, say there is no, we want to get the deflection and we found there is no force there, okay. So, you need not bother, you take a force P, go ahead, okay. You know it will be 0. So, you write the expression in the form of P, you put it there, take the derivative. After taking derivative, at this level you could put it is 0, okay. But if you put 0 at the beginning, you are not supposed to get this one, okay. Right. So, for getting this one, at least at this level you have to keep. After taking the derivative, then only you can make P is equal to 0. Before that, you can't make it. Now, it may be some value, positive, negative, and 0. Up to there you have to maintain. After that, you have to really substitute the value. If there is a problem of say 10 kilonewton, so you have to write P, because you have to take the derivative. You can't take 10 then take the derivative about 10. So, you can't make del u by del 10, you have to give some variable name. So, it will be P. So, at this level you can substitute the value. So, here integration will be only in terms of x, here W, P, everything you can put numerical value, 0 or any non-zero value, then integrate, you will get the value of deflection. Okay. Now, if we take the problem of rotation, slope, we are talking about only deflection. Now, there might be a feeling that this method is valid for finding out the deflection only, it cannot be used for slope, it is also valid for finding out the slope. And we will take a case like this, where there is no direct load under this. So, if we want to get slope, so what should be the corresponding force? There should be a moment, and if we take a case where there is no applied moment, so same problem we can take. Right. So, it has L, E, I, these are all. Now, what will be the rotation at this point we are interested? Now, here just we will put something, say MB, say if it is A, if it is B, I could put it is M, but we will write expression of M as M in order to have a different notation. Say this end is in A, this end is B. So, there we put MB, and we know this value should be equal to 0, but we have to put that and we have to get the expression for the bending moment. So, expression of M at any station, it will be MB omega. So, your U half so just write MB now. If we calculate delta, it is basically du by, here it will be MB. Okay. So, we are interested for finding out the slope at B. Corresponding to slope, we are supposed to give some moment M. So, it is at B MB. So, this delta here is nothing but your, we can write it is rather write theta B. So, theta B will be du by dMB. Now, this half 0 to L. So, this part will be MB omega x square by 2 into 1 into EI into dx, and there will be a 2 that we can put outside. So, this 2 we can cancel. Right. So, square 2 into this quantity, and if you take derivative about MB, MB is MB. So, it will be 1. Now, MB we have to carry at least for getting 1, otherwise if that is not there, whole thing should be equal to 0. Now, you can keep MB, or we can make MB is equal to 0 at this level and perform the integration. Okay. So, if MB is 0, this part will not be there. So, remaining part we can take. So, this will be equal to integral 0 to L omega x square 2 EI dx, right. So, it will be x square means x cube divided by 3, and if we put the limit omega L cube 3 into 2 6 EI. I think this value also we can check. So, distributed load slope omega L cube by 6 EI, right. Now, here after this level MB we have made 0. So, only one term we have kept, and we are getting this value. So, this problem we are interested not deflection, it is slope, and there should be a moment. First of all, we should know there should be a moment there. So, force is corresponding to displacement, and moment is corresponding to slope. So, there should be some corresponding moment, and there is no moment. So, we have put arbitrarily one moment mb, though the value is equal to 0. We have processed that, and finally, we got the value omega LQ by 6 Ci.
So, before integrating mb, you already considered it as 0.
Yeah. Not assume, it is actually 0. So, at this level, we can afford for putting the value mb is equal to 0.
So, sir, for finding slope, we should take a moment. We can find out at that point.
So, there are two aspects here. Number one, for getting deflection, we have to find we have to think for a force. There should be a force corresponding to that. So, in that direction, we want a displacement. There should be a force in that direction. If we want to get a slope along this, so there should be a moment along this. If there is a force or there is a moment, they are fine. We can go ahead, but that should be in a variable form, and finally, we will actually put the real value of that. It may be 10 Newton or 100 kilonewton meter. But if it is not there, we have to take the thing in the variable form, but the end we have to put that is equal to 0. So, this level or up to this level it will be there. In the next level we can make it 0. This level or at the end also we can make it 0. So, if you do not take that, this is 0 at this level, it should be mb into x. Integration after putting the limit, it should be mb into L. It should be mb into L. Now, you could put mb equal to 0. So, finally, it should be 0. Or if you retain, there should be a case combination. There is a moment, there is a distributed load. Right. Now, so with that, at least we came to that level that we have to write the expression of bending moment in terms of force or moment, then put in that energy expression, then take the derivative. At that level, we can really put the value of the load and perform the integration. Finally, we will get the deflections. Now, here this energy theorem, what we are doing, you try to observe here, U equal to m square, we are putting it here. So, after taking derivative, this part will be there into this one. Now, what is this quantity? This quantity is basically m. This one. So, this was m square. So, after taking derivative, we are basically getting m, and this part is derivative of m with respect to mb, mb or p, anything, say this one, earlier problem. So, it was m square, this is m, and this part is derivative of this with respect to p.
That means artificial moment or artificial load, against that we are doing.
Artificial or real, it should be the force or moment where we want to get the deformation or slope, right. So, whole thing can be redefined in a little different manner, and from there the concept of unit load will come, right. So, that part we can take care in the next class. Okay. And I was talking, there is a method called unit load method. It is basically derivative of the your unit energy method. So, energy method, if we look in a separate angle, we will get this method which we are trying to define as unit load method. So, it is not a separate method, it is basically energy method, but looking the whole thing is looked in a different angle. idea is to make the treatment much more systematic or much more mechanical. So, we need not start from the very basic thing. So, energy principle is basically its background, but in a different form we want to apply. Rather, I was trying to explain you here this problem we have solved, m square part we have put there, after taking derivative we are getting this plus another component. So, this part was basically the moment and this part is derivative of that moment about that p. Now, if we write here in general u equal to half integral m square ei dx. So, delta we are trying to tell this is du by dp. It will be this half 2 m dm dp divided by ei dx. Okay. So, u equal to half m square ei dx, where this m was say function of p. Okay. So, p I am writing, it is not the p what we have considered earlier, p may be p, mb or any other quantity, right. So, it is a variable. So, if p is some function of, if m is function of p, so m square by ei dx, this part if we take derivative, so it will be du by dp. So, here this m square will be 2m, 2 it will cancel, it will be m, and this part will be dm by dx ei into dx. Now, this part we can write as, this is capital M and this derivative part if we write small m divided by ei into dx.